Now let us introduce the general method. And so the idea is that if we have a linear differential equation, then of course usually it is not of this convenient form. The left hand side usually is not the derivative of the product of two functions. Well, but we can work around using a very clever trick. And so we are going to multiply it by some function mu of t that is called an integrating factor, so that the left hand side becomes of the right form. Right? So in other words, we're going to multiply the original differential equation by this mu of t, so that the left hand side becomes I'm going to skip t, okay? I'm just trying mu y prime plus p mu y equals now the right hand side is q of t instead of g of t. I hope it's not a big deal. So it's mu q, okay? At the same time, we want this to be equal to the derivative of mu y. But the derivative of mu y is mu y prime plus mu prime y. So let us compare what we have. So this must be, let me rewrite it so it's easier to compare. Mu y prime plus p mu p mu y. Now mu y prime here and here cancels out, then y here cancels out. So therefore we have mu prime plus p mu. Mu prime equals p mu. So if we find this function mu satisfying this condition that mu prime equals p mu, and if we multiply our original differential equation, the left hand side and the right hand side, by mu of t, then we are going to transform it to the form where the left hand side is the derivative of the product of mu and y. Okay. So now, is it possible to find it? And here that there is another very beautiful trick, which is to notice that this is a separable differential equation in its own term, right? Because we can write it as d mu dt equals p. P is a function of t times mu. Now we just separate variables and integrate. So d mu over mu equals p of t dt. Integrate. The antiderivative of 1 over mu is ln mu equals the integral of p of t dt. So mu itself is e to the power integral of p of t dt. Wow. Okay, so that's the formula for the integrating factor. And it's very easy to verify that indeed this mu satisfies this differential equation. And so if you differentiate it, then you're going to get mu itself times p of t. Now, let us review. So the first step to solve the differential equation y prime plus py equals q is to compute this integrating factor e to the power antiderivative of p of t dt. And so let me maybe go through it, explain it again, just to make sure that it's very, very clear. So by doing this, we are going to get e to the power integral of p of t dt. Y prime is dy dt plus p of t e to the power p of t dt y equals e to the integral p of t dt q of t. But then the left-hand side is nothing else but the derivative of e to the power p of t dt times y. Right, because if you differentiate it, you're going to get e to the power p of t dt times y prime plus the derivative of e to the power p of t dt. How do we find the derivative? So the derivative of the exponential function is the exponential function itself times the derivative of the exponent, and the exponent is the antiderivative of p of t dt. So its derivative is p of t and times y. Correct? Correct. Right? So then we're going to get an equation of this form. But then this equation tells us that the derivative of the unknown function mu times y is given. So then to find mu times y itself is just to integrate. So notice that here it is important to find the plus c. So about plus c, you don't need the plus c when you compute the integrating factor, because when you compute the integrating factor, your goal is not to find all possible integrating factors. You just need one particular integrating factor, which means you don't have to care about plus c. But now you need plus c here, because now our purpose is to find all solutions of the differential equation, which means it is up to plus